Geometry lies at the center of a lot of game programming. We use it for game logic, AI, physics, and of course computer graphics. Some games even exploit geometry for their mechanics. A fundamental geometric skill is working with shapes, describing and manipulating them. Think about the last time you created a mesh procedurally or used splines for dynamic roads. There are many ways to do this, and being comfortable with the different methods of geometric thinking is very useful in the design of algorithms, especially in game effects such as the ones we cover on this channel. Hi there, I'm Arman and welcome to Game Logic FX. In this video, I talk about the main ways you can use to describe shapes, how they relate to each other, and when each approach is convenient. These ideas underpin the algorithms we used in all our videos, so I wanted to point this out more explicitly, as it will help you design visual effects too. What are shapes? Shapes are sets of points. In games we work in 2D or 3D, so our points are 2D or 3D vectors. Common shapes have an infinite number of points, so we cannot work with the definition alone. But there are other clever ways to describe shapes that we can use. We will look at those central to games. These descriptions of shapes involve points in some way, hinting at the definition that underlies these descriptions. We will also talk about common ways in which we can get shapes from other shapes that we use often in games and especially game effects. After watching this video, you'll know the main ways that we use to describe shapes and where we use them. You'll understand how to manipulate shapes using these descriptions, and you'll understand the relationships between the different descriptions. Let's first look at ways to get new shapes from existing shapes, so you know what I'm talking about later. Boolean operations occur in 3D modeling tools and vector editing software. They're named after George Boole because they behave like the logical operators that he invented. These are really set operations. Remember, shapes are sets of points. Later, we'll see the link with Boolean logic. The inverse shape is all the points in the space that are not in the shape. The union of two shapes is the set of all points that lie in either shape or in both. The intersection of two shapes is the sets of points that are common to both shapes. The symmetric difference between two shapes is the set of points that lie in either shape but not in both. The difference between one shape and another is all the points in the first shape that are not in the second. Two other operations occur frequently: the Minkowski sum and the Minkowski difference. They're named after Hermann Minkowski, the geometer who invented them. The Minkowski sum of two shapes A and B is the set of all points you get by adding points from A to points from B. If we take any point in A and any point in B, their sum is in the resulting shape. Put differently, for each point in A, we translate the points in B by this amount. All these translated copies are in the final set. We can think of the Minkowski sum as the union of all translated copies of B, where the offsets are in A. Or the other way around, they're the same. Sums for squares, cubes, circles, and spheres are the most common. This table shows a few. A max filter, also called dilation, applied to a white shape on a black background gives the Minkowski sum of the original shape and a square. Remember that the max filter replaces each pixel with the maximum value of a square block around it. Check the outline video where we explain it and use the difference of two max filters to generate shape outlines. Vertex extrusion, another technique we use for creating outlines, is a close approximation of the Minkowski sum of a 3D object and a small sphere. The Minkowski difference between shapes A and B is all the points x such that if you translate the shape B by x, it fits entirely inside the shape A. In other words, it's every translation you can apply to B so that B stays within A. If A is a room and B is a robot with its wheels in the center, then the Minkowski difference is the shape that describes where the robot can go, assuming that it can't turn. The same way the Minkowski sum can expand the border of a shape, the Minkowski difference reduces the border. Here are some differences between a few shapes and squares and circles. Applying a min filter, also called an erosion, to a white shape on a black background gives the Minkowski difference of the original shape and a square. The third set of shape operation is transformations. As a game developer, you probably know the Euclidean transformations, translation, rotation, and scaling very well. We also frequently use polar transforms, transformations that turn lines into circles and vice versa. If you're interested in building your intuition for transformations, there is a fascinating and mind-boggling game, Tandis, that you must check out. We will not delve too deeply into transformations in this video, except to make these important points. You can apply a transformation to the points of a set to create a new set, a new shape. When a shape is described by a function with points as inputs, we can apply transformations to the inputs. Applying a transform to the input points results in the inverse transform being applied to the output shape. If we apply a sequence of transformations to the input points, then we actually end up with the inverse of those transformations being applied to the output in reverse order. For example, to move a circle to the left, you shift all input coordinates to the right before evaluating the circle function. If you apply multiple transformations like rotate then scale, the inverse must be applied in reverse order, scale inverse then rotate inverse. In our video on crosshatching, we used this idea to transform strokes. Check out that video for a more thorough explanation. This idea comes up again and again. It would be worth mastering it. Shapes are sets of points. Can we simply list the points? Well, sort of. Point clouds are lists of points that represent shapes. Usually, we don't list all the points that make up the shape, but rather a sample that is just big enough to simulate or render the shape. Each point represents a small piece of the actual shape. Point clouds can be used for solid 3D shapes, surfaces, 2D shapes, or curves. Point clouds are often the first result obtained from object scans. These are then processed into meshes for applications. Point clouds become powerful when we add physical properties to each point: velocity, mass, and lifespan. We can simulate the physical and fantastical as we dynamically deform the shape that we are depicting. We call this a particle system. In games, we use them for shape-shifting real-world clouds, billowing smoke, flowing liquids, dancing flames, and other things with amorphous shapes. In Scanner Somber, the point cloud is the main mechanic. You explore the world using a scanner gun that reveals the shape of the world through colored points. After points, segments are the next simplest geometric objects. We can represent a segment by its endpoints. So the next idea is to describe shapes using sets of segments. These sets are wireframes. These descriptions were used in some of the earliest games that featured 3D graphics. They were easy to render on vector displays since these devices could only draw curves and lines. Early wireframe games often had no hidden line removal, meaning you could see all the edges, even the ones behind objects. We still use visible wireframes for stylized rendering or debugging, but now we derive them directly from polygon meshes. Some computational geometry algorithms still operate directly on sets of edges. The triangle follows the point and segment as the next fundamental building block. We represent the triangle efficiently by its 3 vertices. Polygon meshes are sets of triangles. Polygon meshes are the principal description of shapes used in 3D games today, and the hardware and software are built around processing polygons efficiently. Describing shapes as polygons makes it easy to render surfaces. The bulk of computer graphics is about rendering these surfaces. Early games that use 3D meshes include Driller and Carrier Command. The core idea in our field is to include normals with a mesh description. Normal vectors indicate the direction a surface faces at each vertex. By interpolating between normals in lighting calculations, we create the illusion of smooth surfaces, even when using only a few triangles. Virtual Racing was one of the first games to use normal interpolation, but Quake really popularized the technique. We can also use sets of cells, like grid cells, pixels, or voxels, to define shapes. For small shapes, such as the tetramenus of Tetris and its countless successors, the list can be used directly. But for large shapes, we need to compress the description. For example, voxel-based shapes can be represented by rectangles or cuboids that make up their borders, as seen in Minecraft or games built with a voxel farm engine. How do we deal with smooth curves and surfaces? Before René Descartes introduced coordinate systems in his groundbreaking La Géométrie of 1637, mathematicians had to describe point sets through geometric relationships. It was difficult to do calculations involving curves and surfaces defined in this way. Coordinate systems revolutionized geometry by organizing space and assigning each point a simple list of numbers, the point's coordinates. This shift enabled geometric problems to be solved using algebra and later calculus. Remarkably, it took another 200 years before William Hamilton's work on quaternions fully connected coordinates with vectors. Before that, vectors were understood primarily as quantities along specified lines, not as quantities with components. Coordinate systems and vector math make it very easy to do geometry with computers. There are many other ways to do geometry on machines, but coordinate vectors are the backbone of contemporary computer graphics. One way to describe sets of points is to express a relationship between the coordinates using an equation. These equations give us remarkably compact descriptions for a variety of curves and surfaces. Equations can also relate coordinates to other quantities called parameters. These equations are known as parametric equations. Linear interpolation, or LIRP, is probably the single most important math operation in game development. It uses the parametric representation of a line to blend between 2 points. The parametric equations of the circle are also used frequently, from procedural mesh generation to visual effects. We used them in our cross-hatching video to do the polar transformation to create this hatching style. Curves use a set of control points in their equations. These concepts are wonderfully explained in Freya Holmer's beautiful videos. See the links in the description. We can write equations in vector form. Here is the circle's vector equation. Vectors can also be parametrized. Here is the circle again in this form. What about describing points inside curves or solids inside surfaces? Inequalities provide a powerful solution for describing shapes that lie on one side of another shape. A disk lies inside a circle, a ball inside a sphere, a half plane on one side of a line. Although we can write the same inequality in many different forms, if we manipulate it so that we have 0 on the right side, we can combine shapes easily. Here are some common shapes written in this form. You can get the inverse shape by changing the sign. Suppose you have two shapes described by inequalities in this form. We can get their union by taking the minimum of the functions to create a new inequality like this. For their intersection, we take their maximum. We can get their symmetric difference by multiplying them together. Finally, we can subtract shapes by computing the minimum between one shape and the inverse of the other. We use the same trick in 3D to describe solid shapes. Here are a few primitives. What if we just need a fast check to see if a point is inside a shape? A function that returns whether a point is in a set is called a membership function. Some of the descriptions we saw before can easily be turned into membership functions. We can query a set to see if it contains a point through the contains function. And we can check whether a point satisfies an equation or inequality. Membership functions are particularly useful when they are fast to compute, such as those for half planes and half spaces, consisting of a simple subtraction and dot product. We can compute unions, intersections, and differences efficiently using this representation. This is where the link between set operators and logical operators comes in. We get the shape complement by taking the logical complement of the membership function. We get the union by taking the OR of the membership functions of the two shapes. For the intersection, we take the AND of the membership functions of two shapes. For the difference, we take the AND of the one shape's membership function with the complement of the other shape's membership function. And we get the symmetric difference by taking the exclusive OR of the membership functions of the two shapes. As you can see, there's a direct relationship between set operators and Boolean operators. Quadtrees, octrees, and KD trees are among the many data structures that we use to implement membership functions for complex shapes efficiently. Membership functions are the mathematical foundation for reasoning about space, so they are really important in game logic, physics, and AI. Membership functions can be encoded as textures, white for points inside the shape and black for points outside it. We usually call these masks and use them to limit the application of an effect. We can extend this with fuzzy membership functions. Instead of assigning strictly true or false, we assign a degree of membership between 0 and 1. An important application is to anti-alias masks, using color depth to create smoother edges and improve perceived resolution. Combining membership with shape operators creates a powerful system to describe complex shapes. In 3D, this is called constructive solid geometry, or CSG. It was popular in early 3D games, especially for level design, and was built directly into game engines. Models using CSG were called brushes, and were the standard format in landmark games such as Unreal, Half-Life, and even Portal. Brushes have now largely been replaced with polygon meshes. What if we need a series of expanding shapes? This is what signed distance functions, or SDFs, do. Developers can use them to create very interesting effects, as we can see in the remarkable Clay book, where SDF-based algorithms allow players to deform anything in the Clay sculptured universe, even themselves. Signed distance functions have a rich mathematical foundation that we can't fully explore here, but I want to explain the basic ideas so you can see how they connect with other descriptions, and how they are used in many game effects. We use this scheme to represent a series of shapes. Each point in space is mapped to its shortest distance from a reference shape. The sign indicates whether the point is outside or inside the shape. This is the sign distance function representing the circles around the origin, where the reference shape is a circle of radius 5. SDFs can be represented as formulas, but they can also be represented as 2D or 3D textures. Here is the SDF from before. Mid-gray marks the reference shape. Lighter shades lie outside and denote positive distances. Darker shades lie inside and denote negative distances. We've chosen the maximum distance as 5 units. So white is 5 units out, black is 5 units in, the center. We can get a particular shape by converting the SDF into either an equation or an inequality. In our example, we can pick a circle by choosing all points with a certain distance value. This gives us a circle with points that are 3 units away from the reference circle, that is a circle with radius 8. And this gives us a circle with points that are 3 units away from the reference circle, but towards the inside, that is a circle with radius 2. We can get a circular disk if we pick all points below a certain value. This gives us a circular disk with radius 8. We can combine equalities to get rings like this. Here is a ring with width 4, and here is a ring with width 6, with a reference shape in the center of the width. We can shorten this last inequality using absolute value notation. In this form, we can think of the resulting shape as adding a width around the reference shape. A 2D SDF turned into an equation gives us a curve. The related inequalities gives us the shape inside or outside the curve, depending on the sign, and combining those gives us a ring around the reference shape. The same idea works in 3D. Then the distance field is 3-dimensional too. We can represent it with a 3D texture or as a function of x, y, and z. A 3D SDF turned into an equation gives us a surface, and the corresponding inequalities gives us the shape inside or outside the surface, and if we combine them, we get a surface with a thickness. Now, the power emerges when we manipulate SDFs to make new shapes. Flipping the sign of the field gives us the inverse shape. The inside becomes the outside. The field created by taking the maximum of 2 fields at each point is the intersection. The field created by taking the minimum of 2 fields at each point is the union. We get subtraction of one shape from another using this. And the symmetric difference is this. This is how people make very complex scenes using just SDFs. We often ignore the sign of distance functions. We are usually more interested in either the inside or outside of a shape, so SDFs are really just fuzzy shapes. We informally used SDFs in all the effect videos we published so far. We use an SDF to control the hair strand thickness in the shell texturing video. An SDF controls the size of the dots in a halftone dithering pattern. The jump flood algorithm computes an SDF that we can use to calculate an outline. In the cross-hatching video, we used an SDF to control the thickness of strokes. And in the watercolor video, we used it to make a smooth shape slightly wobbly to resemble watercolor washes. In all these cases, we got a crisp shape by applying a threshold. The threshold value determines the distance from the reference shape. Surprisingly, the difference of Blur's algorithm to create outlines is essentially an SDF algorithm crudely approximating the jump fill algorithm. The key here is that blurring a silhouette gives us a rough SDF with the silhouette as the reference shape. This means blurring a silhouette is sufficient to create many effects, and we can get rough SDFs easily with shaders or image editing software. We don't necessarily need to use distance. Metaballs, the blob merging technique used in Spore for its creatures, use fields where each point represents an influence value that drops as it gets further away from a reference sphere. The drop-off is not linear, much like gravity and other force fields. In this video, we looked at ways to describe shapes: sets, equations, inequalities, membership functions, and sign distance functions. Each approach builds on the last. Sets are the foundation, the idea that the shape is just the collection of points. Equations gives us precise ways to describe those points using algebra, while inequalities expand that to include entire regions like disks or volumes. Membership functions translate these ideas into fast logical checks, perfect for real-time applications like collision detection or masking. And sign distance functions go even further, capturing entire families of shapes. If you enjoyed this video, please like and subscribe, and remember to hit the notification bell so that you don't miss the next video. Thanks for watching, see you next time.